Okay, so problem 35. Find all the values of x for which the function is differentiable. Okay, and what we're given is a piecewise function, and that piecewise function for the function g of x is equal to x plus 1 squared when x is less than or equal to 0, x plus 1, or 2x plus 1 for when we're between 0 and 3, and lastly 4x minus x quantity squared for when we're greater than 3. Right. Okay. So let's talk about what we know here. In the big span of infinite number of points that are less than 0, do we think the graph of x plus 1 squared, do we think it's smooth? As smooth as Edmund? More smooth. No corners, no cusps in a standard quadratic. We're good. So all those values less than 0, they're all good. What about on this piece of the curve where it's linear? Also smooth? All those tangent lines exist, we're good there. What about on this last piece, which is again next to the quadratic? All smooth. So in the big intervals, we're okay. What about where the two pieces come together though? The question is, are the right-hand derivatives equal to the left-hand derivatives? What we know. The right-hand derivative as we approach 0. The right-hand derivative as we approach 0 is going to have what value? Okay, take 10 seconds to talk to your partners about the slope that you find on a line and how to look at an equation of a line and find its slope. Go.
I know. It's like y equals mx.
Okay. Coming back up here. So when I look at this middle function, where are all the slopes coming out of this middle function? 2. Right. So we would say the right-hand derivative as we approach 0, at 0, is going to be 2. What about the left-hand derivative? What kind of slopes are coming out of this bad boy as we come close to 0? Is it going to be 0? How could we do that? Hey, there's a couple of things we could do. We could use numeric derivative, or we can use the limit as h approaches 0. Which one do you want to do? You want to do the second one? Numeric derivative? Yeah. Okay, then go ahead. Go on the calculator, do a numeric derivative, work with your partners, make sure you know how to do a numeric derivative of the function x plus 1 quantity squared, and I'm interested in what's going on when x is 0. If you need some help, it looks like that. What's that?
I like getting that on the upgraded version, much better.
Yeah, on the upgraded version it looks like this. How's that?
Yeah.
So, someone said 2. Sure. So we have a right-hand derivative of 2, we have a left-hand derivative of 2. This is all at x equals 0. The two derivatives are the same. We need to check one other thing. No?
Is it a custom?
No, we already know if these two curves meet, they meet smoothly because they have the same derivatives coming from both directions. What we don't know is, do these two curves meet? Oops.
Don't need to write.
That's what, earlier today I said poop. Gosh, I'm glad we're recording this. As x goes to 0 from the left-hand side, what value do we get? As x comes to 0 from the left-hand side, what value do we get? 1. So they're continuous and they have the same derivative. There is, at 0, at x equals 0, we do have differentiability. Okay, now we're going to do the same thing on that pair. Can someone find out for me the numeric derivative having to do with this function and what value x am I interested in? At 3. Negative 2 says right. Can anyone confirm that? You can't confirm that? Negative 2? Okay. So, if the numeric derivative is here, this is at what? At 3. If the numeric derivative coming at this side is negative 2, and the numeric derivative of going the other way is positive 2, what don't we have then? You don't have matching slopes. The right-hand side and the left-hand side don't match. The derivative doesn't exist there. This is probably a corner. I don't know if we have a discontinuity. At 3 we have 7, and at here we have 1. Oh, we've got a discontinuity as well. Either way, at x equals 3, not this is where you chime in and you tell me the word on the bottom right. Not differentiable. Now, does that actually happen to be the right answer? Great, I'm so glad. At 3. Okay, so there's 35. Any more questions about 35?
Like you said yesterday, could you just pull the 2 down and put it in front so you would know that?
Officially, we haven't covered it yet, so I won't do it that way. But I might as well show you all the other tools that we can use. So, yeah, I know you could. Yes, you could have calculated the regular derivative. Yeah. And I think we start doing the shortcuts in the next section. All right. So 39. What's going on at 39? 39. Let this function be a piecewise function. 3 minus x, as long as x is less than 1, and ax squared minus or plus bx, x greater than 1, where a and b are constants. If the function is continuous everywhere, what is the relationship between a and b? Would you please, with your partners, discuss? Ready? The issues of continuity here and here. In the 2 green areas, discuss with your partners, are those functions continuous? Go.
Yeah.
But here they're putting always that. Putting one thing and A plus B.
Right.
Yeah, but what if actually zero?
I could not have said that any better. Okay. So, bringing you back up here. Are there any reasons why it's not continuous here? No, this is continuous everywhere. Big check mark. How about here? It's continuous everywhere. Where's the only place it might fail the continuity? At 1. Edmund suggests that at 1, 3 minus 1, that's what the left-hand side would equal, would have to equal a times 1 squared plus b times 1. Or 2 is equal to, I'm going to write a plus b. I'm just going to say 1 squared is 1. Hey, that's great. A plus b always has to equal 1. 2. That's the relationship of A and B. They always have to add up to 2. Find the unique values of A and B that will make f both continuous and differentiable. Well, it ends up, well, because they say unique, they're telling us that there's only going to be one solution. One single value of A and one single value of B that make this happen. Oh, this is such an AP problem. Are you ready? Okay. In order for them, we know what the relationship has to be to have them be continuous. What would have to be true for the function to be differentiable? That the two slopes coming into 1 would have to be equal. Well, the slope coming out of here is -1. The slope coming out of here is 2a plus b.
There we go.
Now, I did that using a shortcut that you guys don't know yet.
Wait, isn't it 2a next?
Yeah.
Well, but I'm talking about when x is 1. So the derivative function ends up being 2ax plus b. I can derive this using the limit as h approaches 0, blah, blah, blah. If you really, really want me to do that, I will. That's okay. No, I mean, because we officially haven't learned that. And some people are like, I don't know where that came from. Limit of h approaches 0. F x plus h minus f of x over h. Yeah, I'm going to need a little bit more room, aren't I? Is the limit, if h approaches 0, f of x plus h is going to be, okay, a x plus h squared plus b times x plus h minus ax squared plus bx, and this is all over 2 h's for numeric derivative. Just plain old H. No, we're not doing a numeric derivative. We can't do a numeric derivative because we don't know what A and B are. All right. Expanding. When I expand that binomial out, I end up getting ax squared plus 2axh plus ah squared plus bx plus bh minus. This reminds me when I was in a stage production of Fiddler on the Roof, by the way. at Zeidel's wedding, there's a bottle dance, and I was the bottle dance, and put a bottle in your head. And there's this, big dramatic moment. You got everyone standing in a line, and there's this step. And then put the bottle on your head. He used Velcro. I'm not kidding.
Put it right on your head, didn't you?
Well, actually, what we're supposed to do, we're supposed to cut out a little round hole in our hats. As the thing would say. But what we found out is if you put Velcro on it, and if you fill up the bottle with sand and make it bottom heavy, it's a lot easier. Okay, cancellation step. Are you ready? This ax squared and that ax squared. This dx and that dx. Everything else has an h in it. Cancel h, h, one of those, h. And what are we left off? What are we left with? When we apply the h goes to 0, we have a 2ax right there. So that's AH. When h goes to 0, that goes away. Oh, and plus b. So there it is.
Is it two another minus?
You have two B's.
No, that got canceled out.
This one got canceled out with this one.
Oh, yeah.
That was just me canceling out an H. Left just the B. So, now what do we have? What we have is that A and B have that relationship, and A and B have that relationship. What we have is a system of equations with two variables and two unknowns. What's up? So, we resolve that. Here's 2 plus is equal to A plus B. Do you want to use substitution method or addition subtraction method?
Substitution.
Substitution. What do you want to solve for? I want to solve for A. So if we do that, that means 2 minus B is equal to A. That means negative 1 is equal to 2 times 2 minus B plus B. Or negative 1 is equal to 4 minus 2B plus B. Or subtract 4 from both sides. Negative 5 is equal to negative B, or B must be 5. And if B is 5, that means A must be negative 3. And those are the unique values of A and B that get you both continuity and differentiability. And I'm not kidding, that's nearly an exact problem off of a previous AB equation. No, that was B, not on the calculator section. I mean, I didn't use a calculator to get there. That's a typical non-calculator. There's a lot more non-calculator questions than calculator questions.
Whoa.
There are 2 sections of the exam without a calculator. It's multiple choice is broken into 2 sections. Non-calculator is about 42 questions, and then calculator was about 28 questions a few minutes ago. And then the free response is broken into calculator first, 3 questions, and then non-calculator, 3 questions. So, yeah, 4 sections. 2 of them multiple choice, 2 of them free response. We're gonna do the entire book.
No, is there like a C? I know like our AB.
Yeah, but the AB class would not go and do chapters 8, 9, 10, and 11. They're only going to get through. They'd only get through chapter 7. 10 or 11 chapters, something like that. Yeah, we're going to do all 10. They'll only do 7 of them. Okay, 43. 43, multiple choice. Let f of x equal the cube root of x minus 1 at which points does f prime of a not equal to the end derivative of the function at x at a? I want to say that the cube root function has a vertical tangent. I want to say that the cube root function looks something like this. And it has a vertical tangent at 0. That's the standard cube root function. So our question is, when does this have that vertical tangent? Is this a calculator question? Okay, it's a calculator question. So we could use the calculator to find out where that vertical tangent is by graphing it. Shall we try that? Kind of know it's either going to be 1 or -1, and I'm never quite sure which one ever it's going to be. How do I get the cube root function in here? Oh, math 4, cube root. Okay. And x minus 1. All right, and so if I go zoom standard, yeah, it looks like that vertical tangent is at x equal 1, and in that place the end derivative function would lie to us. So that's how we could do that problem. The other thing I would probably do, if I didn't have my calculator there, I think what I probably would do would be to set x minus 1, the thing that's inside the cube root, set that equal to 0 and solve for x, and I end up getting x equal 1. I think that's how I would do it if I didn't have the calculator. All right. Well, I don't think we're going to get to the next lecture in. So instead, what I'd like to do is I'd like to show you another calculator trick. Are you ready? Okay. Here's another calculator trick. Let's take a function. Let's take a function that we let's take a function that we don't know what the derivative looks like. How about tangent? How about tangent? The tangent function. Oops, got a good X in there. And I'm going to go zoom trig because it's the best for doing trig. So there's the tangent function. And I'm thinking about, boy, I wonder what the derivative of that function looks like. Now, I know what I could do is I could say, well, look at the function's always increasing, so the derivative is always going to be positive. The function looks like it's very steep and then gets to be shallow and gets to be steep again. So maybe I go from like infinity to, I don't know, do you want to take a guess at what the slope is right there? About 1, and then gets big again. Okay, the function is also not continuous everywhere. It's a continuous function. It's continuous everywhere it's defined, but it's not defined everywhere, is it? So the derivative is also not going to be defined everywhere, is it? So where there's those vertical asymptotes, the derivative is not going to be defined. And I need to put between these asymptotes something that's really big, goes down to 1, and then goes back up again. Something like that. All right. So I think the derivative function of tangent looks like that.
So this is a calculator trick.
No, I'm not getting to the I'm going to check our answer with the calculator trick.
And this is graphical.
The black line is the graph of tangent. The red line is what I believe to be the derivative of tangent. Because it goes steep, it gets to be, when it gets here, the slope is about 1. Let's call this by 1 point. and then it gets steep again, it goes back up again. Yes?
Isn't that the
It's like the absolute value.
It looks kind of like the absolute value of secant. That is true. Secant is up and then down and then up and then down. This kind of looks like absolute value of secant. Hey, how about we check our answers to see how well we did? Are you ready? How about we do that? Ready? I am going to go back to my y equals menu. And besides the fact that I can put functions to graph in there, there's no reason why, hitting the math button, I can't throw into the y equals menu the end derivative. I could say, hey, why don't we take the end derivative of, yeah, it's really full. So, why don't we take the end derivative of tangent with respect to x, and instead of putting a value in there, I just put x in there and whenever we get an x as we're doing the graphing, x takes up. Don't worry about it. Go ahead.
You're gonna keep it that up.
No, it's okay. Because, you know, you doing the recycling and it being on the recording is really cool.
Recycle, guys.
Or gals.
Okay.
There you go.
Thank you.
Thank you. Whoa, how did my keyboard pop up there? All right, close the keyboard. So, I'm going to call the derivative function inside the graphing window, and if I hit graph, and you have to forgive me, it's really slow because it's doing a lot of computations calculating each one of those numeric derivatives. But indeed, we can say, given a function, we can say, tell me what the derivative looks like. It doesn't tell me what the derivative function is, but it does tell me what the derivative function looks like. Slightly useful. Thanks. And how did we do? Does our graph match? Yeah.
Wait, can
It ends up being it's secant squared. So it does look like secant, but in squaring it, we only get the positive value. So it ends up being secant squared. But we're actually gonna prove that later. Yeah.
Can you go back to the Y1 window? And just
Sure. And deriv, the function we want to take the derivative of, comma, x, comma, x. So that's a nice little trick. And by the way, for Edmund, because he had this question before, if I change this to this first function to e to the x, and I go here and I change this function to e to the x, and just so that we can see the difference between the function and its derivative, I go to fat line there, zoom normal. Here's the graph of e to the x, and there's the graph of the derivative of e to the x. And what do you see? You see that they are the same curve. That e to the x has itself as its own derivative. So it's a nice little exploration tool. All right? Okay. I'm going to close off the recording then.